Okay, so you can have this, you can see this lecture later if you need to. Okay, so this is our second class here, lecture number 2. Today is the, yes, Annika, you said you have a hand raised.
Yeah. I was gonna say that like I noticed for the last lecture, there was a mistake with the first problem, like after I reviewed it.
Okay. Okay, which one? What happened? Where?
Um, for the first question, it should be 9b to the third instead of 9b squared.
9b to the oh, you're talking about this one here.
Yeah, the yeah,
You're saying that should be 9b.
to the
How
third
how come?
power.
How come?
Because when you multiply the exponents, it like it would become b to the third instead of like b squared. Like like how you did the first part is like
Mhm.
uh it would be 12 a to the fourth b is correct, but like the second part it should be um 3 times 9 is already 27. A squared is correct, and b times b to the squared is b to the third.
Yes. So that's right, right? Did you see how you said that you're saying that it's correct because you're distributing this back, right? And you get exactly what we started with. So this is correct. Do you see that? So remember, whenever you talk about the GCF, right, and you look at the different terms, you always look for the smallest exponent. So for example, if I want to factor out what's the greatest common factor between a to the fourth and a squared, it's always going to be the smaller exponent, so it'll be a squared. And if you look at b and b cubed, what's the most that I can factor out of both? It's just a single b.
Oh, okay.
Yeah, so no, that's fine. Um, but you literally explain exactly why it is correct.
Oh, okay.
Okay?
I get it.
Well, thank you though. Thank you for that comment. All right. So we did a bit of factoring last time, right? We covered GCF, difference of perfect squares, the AC method, a factor by grouping, right? Those are the major ones that you guys should know. And now we're going to continue with the review. So this is like a review continued. And particularly it's a review of Math 115, which is the class that precedes this class. And we're going to be talking about simplifying, and particularly simplifying complex or called complex or compound fractions. And these are the fractions that have fractions within the fraction. So you have one big fraction and you have smaller fractions within it. Now the question becomes, how do we simplify it? And when we mean by simplify, the goal here, my goal is to um, have a result as a single fraction. So the goal of simplifying here is that this whole complex fraction becomes one single fraction with the numerator and denominator. Now, does anyone remember, or can anyone tell me, what is the first step, or what is the first order of business here when I want to start my simplification of this? Where do I begin?
Do you multiply by the reciprocal?
Say that one more time.
Multiply by the reciprocal?
Multiply by the
Negative
reciprocal.
reciprocal?
Okay. So that would be the case. So that's a good point. So you multiply the reciprocal multiply by reciprocal when dividing by fractions, right? Dividing by a fraction, sorry. Example. So if I do like 4/5 divided by 3/4, then this would be 4/5 multiplied by 4/3, right? And this would be 16 over 15. So in this problem here, I took the bottom equation and I flipped it, right? Flip. This is also known as the keep, change, flip method. That's how we divide by fractions. But we're not going to do that here, as you can tell, because this looks a bit more complicated than having just two regular fractions being divided by one another. So this takes a little bit more. So it says find the GCF. Alexander, yes. Last class we only had 22 minutes. That's all we had to that was recorded. Find the GCF. So CHAM, not exactly the GCF. Multiply the top and bottom by x squared to have common denominator. Common denominator, find the LCD, and that's right. That's right. Thank you, Cindy. The most important part here is to find the LCD. So the step number one, whenever we want to simplify a compound fraction, step number one is find the LCD among, the LCD, which is known as the least common denominator. So that's step one. And if you'd like, right, you can make everything in here, and everything that you see, you can make it into a fraction. This is already fractions, right? And the ones, you can make it a 1 over 1 if you need to see everything as fractions. Now, what do we do? We're going to look at all of the, we're going to look at all the smaller denominators, right? And we can include at 1 as well if you'd like. But 1 is just kind of just there for now. And we look at all the smaller denominators, x and x squared, and then we ask ourselves, what is the least common denominator or the least common multiple? What is the least common denominator among x and x squared? And the least common denominator is x squared. Now, once we have the least common denominator, what we're going to do is step number 2. Is multiply the numerator and denominator by the LCD. So, and then my numerator, I have 1 minus 1 over, 1 minus 3 over x, all over 1 minus 2 over x, minus 3 over x squared. And then what I'm going to do is I'm going to take this whole thing here, multiply it by x squared. Take this whole thing here and multiply it by x squared. Do you see that? In a sense here, I'm not just changing this for the sake of it. When I multiply an expression by x squared over x squared, I'm really multiplying by 1. So the point is that I'm not really changing inherently what this expression is. I'm just changing the way it visually appears. So if I multiply by something very convenient, that's convenient for me, in particular x squared, the reason why I multiply by x squared is you'll see that by multiplying by the LCD, when I distribute this, nice things happen. What happens? Well, when I distribute x squared with 1, multiply by 1, I get x squared. And then when I multiply this here, I get 3 over x, right? But I'm have to multiply this by x squared. And then I'm going to do the same thing again, right? I'm going to multiply by x squared on the bottoms and distribute. And I get x squared, and x squared. And I just want to make sure I keep the color system here correctly, because I want you to see that what happens is when you distribute the x squared, the denominators all get canceled out somehow, right? Because when 3 over x, when I multiply by x squared, I can also consider that to be a 1 over 1. And what happens is some things cancel. The x divides into x squared x amount of times. So then look what's left in the top. On the top, I get an x squared minus 3x. And I have no more fractions in numerator anymore. My numerator is just simply a polynomial. And then what happens in the bottom here, I get x squared minus, again, the x's here cancel. I got an x squared on top, and then I have an x on the bottom, so they cancel, and I'm left with 2x. And then the x squareds here completely cancel, and I'm left with a minus 3. So guys, this is an extremely important step here. Step number 2 is multiplying by the LCD. And when I do so, what happens is I clear the denominator. So the goal of this is to clear the smaller denominators. So in effect, I already completed my goal, right? I want this to be a single fraction. I did it. This is now a single fraction. However, we always want to see if it's possible to simplify further. So once I have my single fraction here, step number 3 is to simplify, if possible. And when we want to simplify, we want to see if we can factor. So you see how these skills build upon one another? So Felipe, yes, so Alexander, that's right. X was the LCD. I just saw it now. And x minus 3, x plus 1. So you're already factoring the denominator, right? So yeah, so we can factor the denominator. We can factor the numerator as well. So when we factor the numerator, we factor out an x, and we get x minus 3, right? Because my GCF for the numerator is just x. And then in the denominator, we have this trinomial. And what adds to -3 but what multiplies -3 but adds to -2. So it would be -3 and +1. So it would be x minus 3 and then x plus 1. You guys see that? So I factor the numerator, factor the denominator. And then once I realize, hey, I have an x minus 3 in both the numerator and denominator, so I can cancel those out. And what I'm left with is x divided by x plus 1. And so this is my final answer here. So what I just did was I got my complex fraction. I found the LCD. I multiplied the numerator and denominator by the LCD, which in fact clears all of the smaller denominators I originally had. So now I have a single fraction. And once I have that single fraction there, I want to see, hey, can I simplify this further? Is there anything else that I can cancel out? And so I have to factor. And I factored the numerator, factored the denominator. I found an x minus 3 in both the numerator and denominator. I can cancel that out, and I'm left with x over x plus 1. So any questions about simplifying complex fractions? Again, this is a review. Are we good with this? Okay. So I hope everyone is clear with how to simplify complex and compound fractions. Because this will appear again. This will pop up again. All right, great. So there's a lot of people that are saying yes, people that are happy. Okay, good. Now, that's simplifying compound fractions. And of course, we can go crazy with this. We can do several examples, but for the sake of time, let's see what else we have. So second kind of thing that I want you to be able to simplify are exponential expressions. Exponential expressions. In particular, I want you to be able to do a deal with fractional exponents. So when I'm talking about like having fractional exponents. Negative exponents. Yeah. And it will all related to all of this is the laws of exponents. So these are an essential skill to understand laws of exponents. So just to remind us, one of the laws of exponents, right? So if we have, for example, x to the a times x to the b, we have the same base, so we add our exponents, right? And the second guy is when you have x over a divided by x over b. This is x. This is when you divide two exponential expressions with the same base. You subtract the numerator with the denominator, right? Right. These are all things that, right, Emily. We subtract, and we also have the rule where we have x to the a raised to the b. So that's when you multiply. When you have a power raised to a power, you multiply the exponents. And there's several more. If you have x to the negative a, so you have x raised to a negative exponent, you can make it positive by putting it 1 over x to the a. That's the one that we have as well. If you have 1 over x to the negative a, so if you have a negative exponent in the denominator, we just move the whole thing to the numerator, and that makes it positive as well. If you have another one, if you have a fraction, for example, if you have like x over y raised to the negative a, then how do you make that expression having a positive exponent? You just flip the fraction like so. So these are like the major laws of exponents. And of course, you also should know that any base raised to the 0 power is equal to 1. And this is when a is not equal to 0. So if my base is any number other than 0, and you raise it to the 0 power, you always get 1. 0 to the 0 doesn't mean much, doesn't mean anything. It's just like an indeterminate form. So you don't have to worry about that particular example. So for now, that should be good. And then there's also a connection between fractional exponents and radical expressions. So there's a relationship that you also should know. Relationship between fractional exponents and radical expressions. So what is this relationship? Well, it's the following. So if I have a base and I have a fractional exponent, m over n, I can rewrite this as a radical expression where the n denominator indicates the nth root. So the n represents the nth root, and the numerator m represents the power. So you can raise b to the mth power. Or you can write this as the nth root of n, the nth root of b raised to the m power. So this is an extremely important connection between fractional exponents and radical expressions. So I'll give you a quick example about this, just a quick example. So like, what if I have something like this? What if I have like 32 raised to the 4/5? And I want to know what this equals. So of course you can plug it in your calculator. Your calculator would do it for you. But I want to simplify it. I want to evaluate it. And what I'm going to use is I'm going to use this connection, this relationship between a fractional exponent and the radical expression. So it actually makes more sense to write this fractional exponent into a radical expression. So as we can see, n represents, right, the denominator of the fractional exponent, and the denominator indicates what is the type of root that we're dealing with. And in this case, we're dealing with the 5th root of what? Of 32. Now, I'm not going to raise 32 to the 4th power because 32 to the 4th power is a huge number. I'd rather use, sometimes it's going to be more convenient to use one over the other. So you see how these are both equivalent expressions? Just that it will be a lot easier if I take the 5th root of 32 first and then raise it to the 4th power. So now my question will be to you guys, what is the 5th root of 32? What does it mean to find the 5th root?
Two.
Who said that?
Daniel.
Daniel, you said 2?
Yeah.
No, you gotta be like 2 or something.
Yeah. How did you get 2? How did you know it's 2?
Well,
Remember, like, you have to factor it like real low.
I know the
How'd you guys
powers
get-
of two, so
Right. No, you guys are right. So for these kind of things, it's good to know, it's good to have an idea of this is like the developing number sense. And one of those things is knowing the powers of 2. So 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and 2 to the 5th is 32. Now, how is this related to roots? Well, root is the undoing of the exponentiation. It's like the opposite operation. So when you take the 5th root of 32, you're asking yourself the following question. What number, if I multiply it to itself 5 times, is 32? Well, it's exactly 2 to the 5th, because 2 times 2 times 2 times 2 times 2 times 2 equals 32. So that's why this here results in having just a 2. And now that 2, I raise it to the 4th power. Do you see that? So this guy right here becomes a 2, and I raise 2 to the 4th power. And the answer will be 2 to the 4th power. I just saw it again. Powers of 2, 16. So 32, if you raise that to the 4/5 exponent, gives you 16. Does that make sense? This is a little tricky. This is the kind of thing that some students may have some trouble with. Let's see if I can come up with another small example. So what if I get something like 27 to the 4, no, I'll do something else. To the negative 2/3. So now I'm gonna, oh wait, someone had a question? I don't see your name. I see somebody got a question though.
Yeah, I have a question.
Yes.
So does that mean that all that we're doing is like the opposite of like the exponential function? I mean fraction?
Yeah, when you take the root, like think about it, right? So when you say 2 squared, what do you get? 4? But when you
4.
say, hey, take the square root of 4, what do you get? 2. So what is the square root doing? It's undoing the squaring. Same thing, right? Like if I do like 3 to the 4th, if you do that, this is 81. But what is the fourth root of 81? It's exactly asking what number, if I raise it to the fourth power, gives me 81, which is 3. Do you see that?
Oh, yeah.
So
That makes
so
sense.
so taking the root, and you have to understand what kind of root are you dealing with. Are you doing square roots? Are you talking about cube roots, the fourth root, the fifth root, so on and so forth? So when you talk about the square root, so one thing you should remember, for example, 4 to the 1/2 power is the same thing as saying the square root of 4. It's just that we don't really write the 2 and this is called the index of the radical. That number that's right outside the radical symbol, that number is called the index of the radical. It's the index. So that tells you what kind of radical it is, or what kind of root that it is. So if you look at the square root, it does have a 2 in front of it, but because it's so commonly used, we kind of just omit writing 2, and we just write the square root of 4, and that's what you always envision, right? You always identify the square root, that radical symbol, with the square root. But just to be very specific, there should be a 2 in front, but we just don't write it all the time. Okay? Hope that makes sense. So now look at what I have here. What if the root is a decimal? Do we round the whole answer in the end, or can we round before that? What if the root is a decimal? Yeah, the square root of, for example, the square root of 2, like if you want to get into that, this is like 1.414 dot 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 dot. It's not a clean number. This is an irrational number. Irrational is a number that has no pattern, and it's an infinite decimal expansion. So in this case, I actually would not want you to have the decimal version of it. I would just leave it as radical 2. So here, this is like an approximate form here, approximate, and this is the exact form. So if that's the case, if your square root is not a clean number, that, like, when I say clean, I'm talking about like a whole number, then you can just leave it as a radical. Okay. So for example, in this question here, 27 raised to the negative 2/3. So the first thing I'm going to do is I want to take care of the negative version, the negative exponent, and then I'm going to utilize one of the laws. Law number 4. Any base that has a negative exponent can be made into a positive exponent if I put it over 1. So that's what I'm going to do. I'm going to put 1 over 27 raised to the positive 2/3. Right? And now, once I did that decision, once I did that, now let's look at the denominator a bit more carefully, and let's apply the relationship between fractional exponents and radical expressions. So you see here, the 3 indicates that the index of the radical is 3. So I'm going to take the cube root. This is called the cube root of 27. And after that, I'm going to square it. So what's the cube root of 27? What number, when I cube it, gives me 27? Does anybody know? 3, 3, 3, 3. Good. So 3. And then after I put the 3 in, I square it, because that's where the 2 comes from, right? The 2 is the exponent. And 3 squared is 9. So 27 raised to the negative 2/3 is equal to 1 over 27 to the positive 2/3. And 27 to the positive 2/3 is 9. So the answer is 1/9. Did you see that? So make sure we understand fractional exponents, how you connect that with radical expressions, and how we can use negative exponents to simplify things. How does it become 1 over 9? Well, let me say it one more time. So we're trying to figure out what is this numerical value equal to, right? Right now, this looks kind of strange and complicated. Okay, so then I'm going to use laws of exponents to hack away at it, right? So my first law that I realize that I can apply is that, hey, I have a negative fractional exponent. So let's take care of the negative part of it first, and then we'll take care of the fractional part of it after. So the negative exponent indicates that I can make it into a positive exponent because I don't really know how to deal with negative exponents directly. I have to change it to something that I'm more comfortable with, and I know how to take care of things that are raised to a positive exponent. So then 27 raised to negative 2/3, I can rewrite it as 1 over 27 to the positive 2/3, correct? I just applied one of the laws. A lot of this, guys, a lot of this stuff is understanding the laws of exponents and the laws of algebra and knowing when or when not to use it. So in this case, I'm using this law here. So apply the law. I did. I put 1 over 27 to the positive 2/3. So I know for a fact that my answer will have a 1 over it because that's the first thing that I do. That's the first step that I apply, right? So 1 over 27 to the 2/3. Now the question becomes again, what is 27 to the 2/3? So then I take a little detour here and I realize, hey, what is 27 to the 2/3? Well, I'm going to now use the connection between fractional exponents and radical expressions. In this case, rewriting it, the fractional exponent as a radical expression will actually be more beneficial to me than just leaving it as a fractional exponent. So the equivalent version of the fractional exponent, 27 raised to the 2/3, that's equivalent to saying, hey, take the cube root of 27 and square that. So what's the cube root of 27? Well, it's 3. And after you take 3 and you square it, you get 9. So then I can replace 27 raised to the 2/3 power. I can replace this with its equivalent numerical value, which is 9. And so henceforth, the result is 1 over 9 being the expression, being the value of my original exponential fractional exponential expression. Does that make sense? Yeah, so like it's like a two-step process, but you start to see that a lot of these skills and a lot of these different techniques, right? You have to be able to apply them like in a synchronous manner. Okay. Okay, so that's that aspect, but that's not even where I want to get at. I want to get at simplifying exponential expressions. So for example, not sure if this is going to be way too tough, but let's say I have something like this: 2a to the negative 5, b to the 3 halves. I raise this to the negative 4 and multiply this by 8 to the a to the 6, b to the negative 9. Square that and divide it by a to the 4th, b to the negative 8, raise that to the negative 1/2. And I know, this is crazy talk, isn't it? So this is the example that I'm looking for as to let's see if we are all able to deal with something like this. And this is really like, it could be one of those topics that students struggle with. The reason why is because there's no direct, like there's not only one way to do this. There's several ways. There's many ways depending upon what you're more comfortable with doing. So does anybody know where we can start? Again, we can start in many directions, but where should we start? Where could we start? And again, we're trying to simplify, okay? The idea is we're trying to simplify and make everything into positive exponents. Make everything into positive exponents. Okay, so I see GCF and LCD. The LCD is connected to rational expressions. These are exponential expressions. So all these words really do matter. Rational expressions are one kind of expression, exponential expressions are another. So in this case, there's no addition sign, there's no minus sign. It's just multiplication all the time. Okay, so see, I have several suggestions. Chen says to eliminate the negative exponents. Tiffany says multiply the powers first. And then Sydney says move numbers variable with negative exponents. So okay, so we're seeing that there's a common thread here. The common thread is, hey, I have these negative exponents. Boo, no good, right? I don't want negative exponents. And then the problem with the negative exponents is I have negative exponents within those negative exponents. So I have an expression that's raised to a negative exponent, and within that expression, I have negative exponents as well. So things can get very annoying really quickly. So one thing you can do is if you take care of the negative exponents, you have to be very careful with that. So what I'm going to do first is I'm going to apply this rule. I'm going to apply this rule here. So if I have a power raised to a power, what happens is when I have a product of when my base is a product of other exponential expressions and I still have that raised to a power, I can take everything individually and raise each of these expressions by the same power. So this is going to look like the following. So I can take 2 and I'm going to raise that to the -4. I could take a to the -5 and raise that to the -4 power. I could take b, and again, this is all multiplication. So if you don't see anything, if you don't see any operation between two numbers or expressions or variables, then you immediately infer that it's multiplication. So does everybody see that? For this guy here, I'm taking everything inside the parentheses and raising it to -4 power. That's a legal move. That's literally just applying step number 3 here, but for several products, I can do this. So if I can do that, then I can definitely do the next one, right? I look at all of them here and raise that to the second power. So 8 squared, a to the 6 squared, b to the -9 squared. So now I took care of that portion there. Great. Now I have a to the 4th raised to the -1/2 times b to the -8 raised to the -1/2. So all I've done so far is I just rewrote it so that everything inside the parentheses is being raised to the indicated exponent. So any questions about that? So that's all I've done. Okay, so if we're clear with that, so now let's go on to the next thing. Now I'm going to look at all of them individually. So 2 to the -4, 2 to the -4, I have this negative exponent associated to 2. I can make it positive by doing what? By putting it in the denominator. So I can write this as 2 to the +4. Do you see that? So, okay, so I took care of this guy here. I took care of that. Now, a to the -5 raised to the -4, I can apply the laws of exponents. So I can multiply a -5 with -4 and I get positive 20. So this is a to the +20. Now I have to take 3/2 and raise it and multiply by -4. What's 3/2 times -4? Does anybody know? -6. That's right. You can put this 2 goes into 4 twice. 3 times -2 is -6. So we have to know how to multiply fractions, guys. Fractions are important to know how to deal with because it can actually be very useful knowing how to deal with fractions rather than decimals, for example. So far, so good. So I took care of this expression. I took care of this expression. Now 8 to the 6th power becomes 64. A to the 6th squared becomes a to the 12th. B to the negative 9 squared becomes b to the negative 18. So far, does everybody see how I'm taking care of, I'm making this blob, these blobs of expressions, now I'm taking them into smaller little bite-sized pieces and taking care of each one individually. And then slowly things start to simplify out. And then I'm going to do the same thing here. A to the 4th. Why didn't you put b to negative 6 in the denominator? Yes, I can do that. Rita, I can. I can do many things. I can do many things at once, but I'm doing it everything step by step so that I don't lose anybody. Because I can do this and just not even do all the intermediate steps. But I just want to make sure everybody sees where things are going. So eventually, yes, you could put this in the denominator. You could put this one in the denominator and then simplify that way. So we'll see. We'll see how we can further simplify it. And now the denominator, a to the 4th raised to the negative half. I multiply 4 times negative a half, and I get a to the negative 2. So I took care of this guy here. And again, we're just trying to be organized with our work here. And then b to the negative 8 to the negative 1/2, I can multiply negative 8 and negative a half, and I get b to the positive 4. Why did 2 to the negative 4 go to the denominator? Well, because, pardon me, in the beginning, 2 was raised to the negative 4th power. But we don't deal with negative exponents. So we make it into a positive exponent. And the only way we do that is by placing this whole expression into the denominator. So we are applying exponent law number 4. Right. So you see how these laws here, we have to like know when and when not to apply. So if it's applicable, apply it. If it's not, then don't. So for example, here I can apply several laws if I'd like. I can say, you know what? I don't want to deal with anything unless they're all positive exponents. Well, if that's the case, then let's take care of that. So where are the expressions that have negative exponents? Well, this is one, and this is one. So these are all negative exponents. How do you make them positive? Just move them across the fraction. So if we have a denominator that has a negative exponent, move it in the numerator. If you have a numerator portion that has a negative exponent, move it into the denominator. So if that's the case, then we can do that, right? Another thing is I'm going to move the 64, this number here, I'm going to put it in front because multiplication is commutative, which means that I can switch the order around. So 64, usually we place the numbers in front. And in the denominator, 2 to the 4th power is 16. So these are the numbers in front. Now I'm going to be moving a to the negative 2 in the numerator. I'm going to move this to the denominator. I'm going to move this to the denominator. So what's going to change here? I'm going to have a to the 20th multiplied by a to the positive 2 multiplied by a to the positive 12. I'm going to have in the denominator b to the positive 6 multiplied by b to the 4th multiplied by b to the 18. Do you see that? Now all my exponents are positive. And it just so nicely works out that everything in the numerator has a in it and everything in the denominator has b in it. That doesn't always happen, but in this case it does. And now what can I do? I can apply the first rule, right? The first rule is, hey, if you have a product of the same bases, what do you do with the exponents? Well, you add them. You add them all up. And another thing I can cancel out is the 16. 16 goes into 64 4 times. So 16 goes into 64 4 times. So then I get 4. I get a to the 20 plus 2 plus 12. I can add all these up. And I can take b to the 6 plus 4 plus 18. So which rule is that? The rule is the first rule. I can have, if I have a product and two bases that are the same, you add the exponents. In this case, I have a product of three bases that are the same. So I can add all the exponents together. And when I do that, what do I get? I get 4 times a raised to the 34th power divided by b. And this is kind of hard to see. 6 plus 4 plus 18 is 28. So do you guys see how we went from a seemingly complicated exponential expression with all these different negative exponents and fractional exponents? And we did a lot of the laws of exponents. We applied it systematically and step by step so that I get a final answer here. So any questions about this? No questions. Do we have to put the dot between 4 and A? Or we can just write, yeah, so you don't have to. You definitely don't. Like I said, whenever you put two numbers, two expressions, a number and an expression, and you just write it next to one another, the implication is that it's a multiplication. So sometimes I put it, right, just to emphasize that it's multiplication, but you don't need it, so you don't have to. So you can just leave it as 4A, 3 to the third to the 34th, B to 28. Same thing. Okay. Okay, let me just see. Okay, so I hope you guys are comfortable with this. Of course, there's tons to work on if you need more practice with this. In the textbook, there's a lot of examples to go over. But piggybacking off of what we did with the fractional exponents, with the radical exponents, I want to see how you guys do with the following. Can you, for example, can you simplify radicals? So that's another thing we want to be able to do. So step 3 is simplifying radicals. So for example, if I have something like this, so I take like the square root of 125 plus the square root of 45. How do we add radicals? So what's one prerequisite for adding radicals?
You need to have a common number under the radical.
Correct. So it's similar, not the same, but when you talk about adding fractions, you must have the same denominators. When you want to add radical expressions, you must have the same expression under the radical. And how do we get to that point? How do we get the same number underneath the radicals? Yeah, you want to break them down. Good, Sydney. How do you break them down, though? How do you know we have to use 5? So that is a common factor. That's right, Valerie. It is a common factor. But what is the general idea of breaking down, quote unquote, a radical expression using other powers that may multiply to them? Okay. So let's just say this. How do you, quote unquote, break down? How do you break down the square root of 125? Does anybody know how we break it down? Right. See, now we're talking. We have to find two numbers, or what are called factors of 125, but we have to see which one of them has a perfect square, and we want to get the biggest perfect square. So to break down radicals, you want to find the largest factor that is a perfect square number. So what is what are perfect squares? So yeah, so you guys are already on top of it. Very good. But what is a perfect square? Yes. So a perfect square is a number, or I should say it's a whole number that comes from taking another whole number and squaring it. So I know many of us have an idea what it is, and trying to explain it is kind of sometimes interesting. But yeah, the perfect squares, you guys should know perfect squares. So what are the perfect squares? So for example, 1 squared, 1 is a perfect square. Why is it a perfect square? Because we have a number 1 that when you square it gives it 1, that becomes 1. Then so on and so forth, right? That's right, guys. Good. So 2 squared, 4, 3 squared, 9, 4 squared, 16, 5 squared, 25, 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100, right? So all of these numbers, it's not the 10 that's the perfect square. It's the number that you get from taking 10 and squaring it. 100 is a perfect square. And you can, yeah, you can think about like literal squares. You can think about squares whose sides, for example, are both 7 and 7. When you take the area, you take the side and you square it. And that's another reason why people talk about square numbers. They're square because you can think of an actual square that has these dimensions, and finding the area is it results in these numbers. And of course, you can keep on going, right? We can go on forever with this. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is, who knows 14 squared? $196. Okay, good. What's 15 squared?
225.
225. Good. What's 16 squared? 256. 17 squared. 289. 18 squared. 324. 19 squared. 361. And 20 squared.
400.
400. Good. And again, we can keep on going. But guys, it's good to go over this. These numbers, it's good to be able to look at a number like 256 and realize, oh, that's 16 squared. It gives you a better understanding, a better dealing with numbers. So these are the things that you guys should know. You should know perfect squares, what they are. You should know the powers of 2. You should know the powers of 3. You should know the powers of 4 and of 5 and of sum of 6. So like it becomes better. It becomes easier for you guys to deal with just numbers in general, number sense. So 125, as some people have mentioned, right? 125. What are the factors of 125? Well, we notice that 25 is a factor, right? 25 is a perfect square. How many times does 25 go into 125? Well, it does it 5 times. So I can break this down as the square root of 25 multiplied by the square root of 5. But the square root of 25 is 5. Square root of 5 is just square root of 5. So I leave it. So this becomes 5 square root of 5 plus, and then square root of 45 is what? Is 9 times 5, right? Take the square root. But 9 is a perfect square. So I can take the square root of 9 individually, and I get 3 rad 5. So this becomes 3 rad 5. And this is like saying, hey, I got 5 apples plus 3 apples. I have a total of 8 apples. So that's how we add radicals. We need to have the same radical number underneath so I can compare it. If I don't have the same number underneath the radical, then I can't compare them to and I can't combine them, I can't subtract. So that's how we simplify the addition. Does that make sense? So if that makes sense, let's see what happens though when I change the index of the radical. What if I change it and I don't deal with square roots? What if I do something like this? What if I deal with the cube root of 54 and I subtract from the cube root of 16? How do I approach this? What if there's no perfect square that is a factor of the number in the radical? Well, very good question, Rita. If there is no perfect square that is a factor of the number in the radical, then you can't break it down. So if a number has no perfect square as associated with it as a factor, then you just leave it. It's actually easier to deal with because you don't have to break it down. Now in this problem here, oh, okay. So Gabriel, good comment. It's a cube root, but 9 does not have a cube root. Well, let me just say this. 9 does have a cube root, but it's not a whole number. So see how we deal with in the previous example? In the previous example, we deal with perfect square numbers because we're dealing with square roots. In this problem here, we're dealing with cube roots. So what do you think we need to know? We need to know what are perfect, not squares, but perfect cubes. We have to know our perfect cubes. So now in this case, what's a perfect cube? So 8 is a perfect cube. Why though? Why is 8 a perfect cube? Well, take 1, take the natural number 1, cube it. 1 is a perfect cube. Take 2, cube it. 8 is a perfect cube. Take 3, cube it. 27 is a perfect cube. Take 4, cube it. 64 is a perfect cube. Take 5, cube it. 125 is a perfect cube. Take 6, cube it. 216 is a perfect cube. So on and so forth. Take 7, cube it. What's 7 cubed? I think it's 343, right? So on and so forth. 8 cubed is 9 cubed. So what is it now? Why do these numbers matter? Why do I care about the perfect cubes? What's so special now about how helpful is it now that I know these numbers? What's the idea? What's the idea? Right, so we're dealing with cube roots. So we have to break them down. That's right. So then how do I break it down? What am I looking for in this case? You see how in the previous case we said break down square root by finding what? The largest factor that is a perfect square? Very good, Valerie. So now we're going to look for numbers whose factors are perfect cubes. So 54 has several factors, but one of them is a perfect cube. What number is a perfect cube that's a factor of 54? So of these numbers here, what divides 54? And 27 is correct, and 27 goes into 54 2 times. So then I can write this as the cube root of 27 multiplied by the cube root of 2 subtracted from. Now how about 16? What's the perfect cube of 16? 8. And 8 again goes into 16 twice. So I can write this as the cube root of 16 multiplied by the cube root of 2. Do you guys see that? And now the cube root of 27 is 3 times the cube root of 2. And you see 2, I can't break down any further because 2 is not a perfect cube. So I just have to leave it underneath the radical. And this becomes minus 2 cube root of 2. How do you get the cube root? How do you get the cube root of 27 and 2? So okay, how do I get that? Again, I have to look for the factors of 54. But I want to find the factors of 54 in such a way that one of them is the largest perfect cube. What I realize is 54, I can write it in many ways, right? I can write it as factors, as a product of different factors. But 54 can be written as 27 multiplied by 2, can't it? Is it 27 times 2, 54? But why do I care about these two numbers? Because these two numbers, for one of them, 27, that is a perfect cube. Because it's a perfect cube, I can take the cube root of the perfect cube. So the cube root of 27 is 3. So therefore, we say, hey, this is, I can split this up now. The cube root of 27, which is nice, and the cube root of 2, which is not so nice. So I just leave the cube root of 2. This becomes 3 cube root of 2. So what I'm doing is I'm taking the cube root of 54 and simplifying it into something smaller in terms of the number underneath the radical. So the cube root of 54, I can rewrite that as 3 times the cube root of 2. And so now I have 3 times the cube root of 2 and subtract that from 2 times the cube root of 2. So again, it's the same thing that we did yet last time with the square roots, but now it's the cube roots. So now we have the same cube root. We have a 2 in both of the radical expressions. So again, it takes saying 3 oranges minus 2 oranges. I have how many oranges left? I got 1 orange. And what does that orange represent? The cube root of 2. So I can just leave it as the cube root of 2. And that's my final answer. So these are things that we need to know. And what helps a lot with radicals in particular is knowing what kind of radical it is, what kind of root. Is it the 4th root? Is it the 5th root? Is it the square root? Is it the 10th root? Is it the millionth root, right? Those things matter. And associated with that are the numbers that are associated with perfectness. So you have to know what are called perfect squares and understand what those are and being able to identify those. What are perfect cubes and what those numbers are and how do you find those and so on and so forth. What are perfect, I don't know how to call those, perfect fourths, so on and so forth. Those things help us. How did I get 2 times cube root of 2? So Rita, it's the same idea as to why I got 3 cube root of 2 for the cube root of 54. 16 can be broken down as 2 factors, 8 and 2. And I think that's where I made the little mistake. So there's a mistake here. It should be 8. Pardon me for that. Because 8 times 2 is 16. So the cube root of 8, as we notice, the cube root of 8 would be 2. Yeah, that was my mistake. Thank you, Rita, for noticing that. So the cube root of 16, I broke it down as the cube root of 8 times the cube root of 2, and the cube root of 8 is 2. Yeah, no problem. Yeah, guys, just tell me. If you say, hey, this is wrong, just tell me. I have no problems. Now, everything's clear, right? I hope so. Tiffany, no, you don't have to. You don't have to put the 1. You can put the 1, but it's kind of like understood. So a lot of times in mathematics, right, some things are just omitted because it's understood. Same, for example, the square root, right? We don't put the 2 in front. There should be a 2, but we don't put it because it's understood. Indeed, 3 minus 2 is 1. That's correct. But think about it. 1 multiplied by a number, isn't it that number? So 1 times the cube root of 2 is just the cube root of 2. So we just leave it. We don't have to. Nothing wrong with putting the 1 in it, but not needed, not necessary. Okay, so we're dealing with a lot of stuff. Hopefully, a lot of these things are, clicking in your heads. Hopefully there are a lot of refreshers going through your minds of mathematics here. A lot of this is foundational knowledge. You need to have these things well understood, so that the more complex problems that you deal with, the more complex techniques, you won't be bogged down by these details. And algebra really is the language to mathematics. So if you don't have your algebra game on point, then it becomes very difficult as you climb up the ladder of higher mathematics. It really does. And you know what? I just want to complete this. I can't just leave it like this for some reason. So 8 cubed, 9 cubed, and 10 cubed. Let's just complete the cubes. What is 8 cubed? 512. Good. 512. What is 9 cubed? 729. Good. And then finally, 10 cubed is 1000. Okay. Good. Good. So these numbers, you should be able to recognize, hey, these are cubes. And so on and so forth. These are squares, perfect squares. Okay, so now I'm gonna head into probably the harder part, the harder portion of, I would say, simplifying radical expressions. So I'd say these are like a little bit more simple to deal with because these are just numbers. But now the problem becomes, what happens when I have radicals that have what do you call it? Like, what if I have variables underneath? So for example, if I get square root of, let's say, 8x cubed y squared, what if I have to simplify something like this? So in these problems, right, we were simplifying radical expressions that had numbers in them, just purely numbers. So that's doable, that's reasonable, right? But now let's say I have a radical, but it has exponent, it has variables within it. Now, how do we break this down? This is like I said, this is the harder version of simplifying radical expressions.
Separate them into each radical.
You can do that. Sure. So we can say radical 8, right? Radical x cubed and radical y squared, right? So we can do that. But then what? So radical 8, I can break down, can I? By what we've done earlier, right? Radical 8, just radical 8. I can figure out what two numbers multiply to 8, where one of them is the biggest perfect square. That's a factor of 8, which happens to be what? 4 and 2. So I can break down as 4, square root of 4 times square root of 2, which becomes what? 2 rad 2. So we deal with numbers easily. But now my question is, how do you deal with the square root of x cubed? How do I break down the square root of x cubed? The same way we deal with whole numbers. And how is that? So I agree with you in a way that you really do take care of it the same way, but I think you got to deal with it in a much more special way though. That's right, Sydney. But now the thing is, the perfect squares that we know, are whole numbers. They're numbers. Right now we're dealing with a variable. So how do you connect perfect squares with variables? That's the key here. So we know perfect squares of whole numbers, right? We know what those are. I was like, oh, you guys were listing them all out. Great. But what are the perfect squares when we talk about variables? So let me ask this. Is x cubed a perfect square? Yes or no?
No, but couldn't you just leave it as x on the outside and then just x on the inside of the radical?
Very good, Daniel. But how do you know that?
Cause the radical is just by 2, so you just do 3 minus 2. I mean, just take the radical. It's yeah, I just did like 3 minus 2. And then does that work? I don't know if I did the
That's a
right
bad.
math or like.
No. You caught a pattern. Like, but so the real reason why your expression, your steps work is because of the following. It's related to what you're saying, and it's related to what others have said in the chat. X cubed. Remember how we break down? Look, so let's look at 8. Remember how we break down 8? We take 4 and 2. 4 is a perfect square, so we can break down 4. Because square root of 4 is 2. Now, x cubed is like kind of like a different thing. It's like a different species, right? It's a variable that's raised with the power. But you can rewrite x cubed as the following: x squared multiplied by x to the first power, can't you? And then you can break this down as the square root of x squared multiplied by the square root of x. But the square root of x squared is x. In other words, x cubed is the perfect square. And now x squared is the largest perfect square that is the factor of x cubed. Do you see that? So I can break this down as the square root of x squared times the square root of x, and this guy here becomes x times the square root of x. And then by the same token, what is the square root of y squared? It's y, because you're taking the square root of a perfect square. Y squared is a perfect square. And you multiply that, And then what do? Everything that's out, that's not inside the radical, you place it in front. So the 2, the x, and the y are going to be placed all in front. 2xy. And everything that's underneath the radical, you put it underneath the radical. So the 2 is underneath the radical and the x underneath the radical. You can put them all together. So it becomes 2x. Does everyone see that? So the key note here, guys, the note that I will leave with you is that every variable that is raised to an even exponent is a perfect square. Example: x squared, x to the 4th, x to the 6th, x to the 8th. These are all perfect squares. Why are they perfect squares? Because when I take the square root of them, I get something else, right? If I take the square root of this, square root of x squared is x. The square root of x to the 4th is x squared. Do you guys see that? The square root of x to the 6th is x cubed. The square root of x to the 8th is x to the 4th. Because you can think of this as x squared squared. You can think of this as x squared. No, sorry. Yeah, you can think of this as x cubed squared. You can think of this as x to the 4th squared. Does that make sense? And what matters, guys, what matters is the kind of square root that it is. So if it's a square root, then you're dealing with these things. Now, what if I'm dealing with the cube root? What if I'm dealing with the cube root of like, let's see. Yeah, what if I'm dealing with like 16 and this is x to the fourth or y to the fifth? What if I have to break this down? So again, I can take everything individually. The cube root of 16, the cube root of x to the fourth, the cube root of y to the fifth, right? Now, how do I break down the square root of 16? But I already did that. The square root of 16 is equal to the cube root of, the cube root of 16 is equal to the cube root of 8 times the cube root of 2. But the cube root of 8 is 2 times the cube root of 2. So I know this one already. I already know what this is. But now the more interesting thing is how do we break down the cube root of x to the fourth power? In this case, we're dealing with cube roots, not square roots anymore. So what we're concerned with are not perfect squares, but perfect cubes. So then how would we break this one down? Anybody? Anyone? X cubed and x, right? It's still the same idea. I want to find the largest factor of x to the fourth that's a perfect square. Pardon me. That's a perfect cube. In this case, you have to have something cubed. X cubed times x to the first power is indeed x to the fourth. So I can break this down further. The cube root of x, the cube root of x to the first power. So the cube root of x cubed is just x. Does everyone see that? So now this becomes x times the cube root of x. Now, how do we break down the cube root of y to the fifth power? How do you break that down?
Wouldn't it be y to the fourth times y to the first?
Y to the fourth times y to the fifth? Oh, y to the first. Is that what you said?
The first, yeah.
Okay. So you're correct in saying that y to the fourth times y to the first is y to the fifth. You're correct. However, y to the fourth is not a perfect cube. So you have to rearrange that. So really what you meant to say was that it's equal to y cubed times y squared. Again, y to the fourth is not a perfect cube. Y cubed is. And so this is where you have to come up with the reasoning. So the cube root of y cubed times the cube root of y squared. What's the cube root of y cubed? It's y. So this becomes y the cube root of y squared. So the note here, what's the note? The note here is that perfect cubes have variables, have exponents that are multiples of 3. Example, y cubed, y to the 6th, y to the 9th, y to the 12th. These are all perfect cubes. If I take the cube root of y cubed, I get y. If I take the cube root of y to the 6th, I get y squared. If I take the cube root of y to the 9th, I get y cubed. So again, this is like saying y squared cubed. This is like saying y cubed cubed. Okay. So that's why it's not to the fourth power. Does that make sense? And so now, everything that's outside the radical, put it outside the radical. So it's going to be 2xy, right? And everything that's inside the radical, just leave it inside the radical, which is going to be what? 2y squared. And that's my final answer. Okay, so we're getting the hang of this with simplifying radicals. Again, this is just review, and there's plenty of practice to go around with this. Okay, so we're more comfortable with this. So let's see. What about the x in the middle? Oh, thank you, Rita. I completely glossed over that. What is wrong with me? Okay, yes, you're right. There's an x here. So I forgot about the x. Thank you. Thank you for that. Okay. Great. So now that gets a little better, right? That's a little better now. Let's start slow with this. What if I want to add these things together? What if I want to add these? So I have to break them down, right? Individually.
Get the x's on the inside to have the same what's the little thing on the top called?
The same exponents?
Yeah, the same exponents. So have like x squared on the outside of the x5 and then just x, and then you could just add them.
Okay, so that's good. So I'm gonna take each of these individually, break it down. So 16, I can take the square root of 16 because it's a perfect square. So this is 4 rad x. Now, how do I break this down? The x to the 5th power. Remember, we have to find the two things that are perfect, the largest perfect square that's a factor of x to the 5th. And in this case, go back to the note. What does the note say? Every variable that is raised in even exponent is a perfect square. So then the largest perfect square that's a factor of x to the 5th is x to the 4th. And this becomes x squared rad x. Do you see that? And now that's good because I have the same radical. Since I have the same radical, I can unite the two things in front, 4 plus x squared. So then this here becomes 4 plus x squared. That's together. And outside of it is a rad x. So same idea. We want the expressions underneath the radicals to be the same, because once they're the same, you can combine them. You can connect. If they're not the same, you can't do anything. Okay. Okay, so let me give you the last one of these, and then we can move on. We can move on. Now, what if I get something like this to you? I get x squared y, the square root of 20 x to the 5th y to the 7th minus 2xy, the square root of 5x to the 7th y to the 7th plus 7xy squared, the square root of 45x to the 7th y to the 5th. So now you guys are, what is going on? So here we're only dealing with square roots. So that's the one thing is square roots, all we're going to talk about are square roots. Now, the only way we can combine these three different radical expressions is if all of the radicals underneath The expressions underneath the radicals, they're all the same. So can we break them down? So first of all, let's break each of these down. Let's break down this. Let's break down this radical, and let's break down this radical, if possible. So let's look at 1. How do you break down the square root of 20x to the 5th y to the 7th? What is this simplified to or reduced to? Can we break down the square root of 20x to the 5th y to the 7th? That's right. So I can break down to 20. So I'm just going to individually break each of these down. So the breakdown of 20 is the square root of 4 times the square root of 5. But the square root of 4 is 2. So the square root of 20 can be broken down to 2 times the square root of 5. So that we can do that. Now, how do we break down x to the 5th? The square root of x to the 5th. That's right. So I can write this as x to the 4th times x square root of x. But the square root of x to the 4th is x squared rad x, right? And how can we break down the square root of y to the 7th? What does that become? So what's the largest perfect square? Right. So to y to the 6th times y to the 1st, which becomes y cubed square root of y. So this becomes, the final answer is 2x squared y cubed. Take the square root of 5x y. So that's number 1. How about number 2? How about 5x to the 7th, y to the 7th? Well, I can break down each of these down individually. The square root of 5, I can't break down any further. It's not a perfect square, so I just leave it. X to the 7th, I can write this as the square root of x to the 6th times the square root of x. The square root of y to the 6th times the square root of y. And I get the square root of 5 times x cubed times square root of x times y cubed times square root of y. So this results in x cubed y cubed square root of 5xy. So far, so good. So we were just breaking down each of these radicals step by step. And then the last step here is the square root of 45 x to the 7th y to the 5th. So then what do I get? The square root of 45. How can I break down the square root of 45? Five and 9, that's right. So I can write this as square root of 9 times square root of 5. I can rewrite square root of x to the 7th as square root of x to the 6th, square root of x. And I can write this as square root of y to the 4th times square root of y. Again, why am I writing it this way? Because the highest perfect square that's a factor of x to the 7th is just one less than it. It's x to the 6th because it's an even power. Y to the 5th, the highest exponent, the highest factor, the largest perfect square that's a factor of y to the 5th is just one less than it. It's y to the 4th. And that's why we are taking the square root of those things, because there is such a thing as a perfect square of x to the 6th and a perfect square of y to the 4th. So the square root of 9 is 3. This is 3 rad 5. The square root of x to the 6th is x cubed, rad x. The square root of y to the 4th is y squared, rad y. And this results in 3 x cubed, y squared, the square root of 5xy. Woo! So that's a lot of breaking down, right? We've been breaking down things. So, like I said, your algebra has to be on point, on point. So now I'm going to replace everything that I just broke down, right? So for number 1, So I'm just gonna box the expressions for number 1. This is number 1. This is for number 2, and this is for number 3. So I'm going to replace them in the original expression. So I have in the original expression, I have x squared y, and I'm going to replace this with 2x squared y cubed, the square root of 5xy, minus 2xy, and this becomes x cubed y cubed, square root of 5xy, plus 7xy squared, multiply that by x cubed y cubed, square root of 5xy. And now I can multiply, and all I can multiply are the expressions on the outside of the radical. So this becomes 2x to the 4th, y to the 4th, square root of 5xy, minus 2x to the 4th, y to the 4th, square root of 5xy, plus 7x to the 5th, y to the 5th, square root of 5xy. And again, when I multiply, same basis, I just add the exponents. That's why I get the result. And what so nicely happens is that these expressions here are exactly the same thing, and I subtract them. So I'm left with those things being canceled out. And the result is 7x to the 5th, y to the 5th, the square root of 5xy. Isn't the last expression 3? Yes.
Shouldn't it be 7x to the 4th, y to the 5th for the last expression?
You're right. Yes, that's right. That's right. I calculated. That's right. This is y to the 4th. Pardon me for that. And Tiffany said, isn't the last expression 3x to the 3rd y squared? 3x to the 3rd yx squared? You're right. You're right, guys. I'm seeing double. I don't know what's going on. So yeah, this is not right. So this part is not correct. So that means that this part is not correct. So you're right. Thank you, Tiffany. So yeah, this is number 3. Sorry, I should make this clear. This is 1, this is 2, and this is 3. So the third one guy, right? The third guy here is 3x cubed y squared, the square root of 5xy. Okay. So that's going to be a quite different. This will be now 21 x to the 4th, y to the 4th, the square root of 5xy. So this should be the final answer. Let me know if you guys see anything that does not satisfy your own work. So is this clear now? So 7 times 3 is 21. X to the 1st times x cubed is x to the 4th. Y squared times y squared is y to the 4th. So we still have these things that cancel out here. These terms do cancel out, but this is my final answer. Awesome. We're covering a lot of things today. Woo. Hope you guys are having fun out there at the comfort of your home. Okay, so we've talked about simplifying complex fractions. We've talked about simplifying radical expressions, exponential expressions. So we've done complex fractions, exponential expressions, radical expressions, which is very good. And I think we're gonna finish. I don't know if we have. Probably can do a bit more. We're gonna talk about rational, simplifying rational expressions. So we have rational expressions, exponential expressions, radical expressions, and all these things we're trying to learn how to simplify. Okay. So what are rational expressions? Rational expressions are just ratios of polynomials. That's what they are. Ratios of polynomials. And how do we deal with them? Well, a lot of this stuff deals with knowing how to factor. So a lot of it is just factoring. Let me see if I have some good problems for you guys. Yeah, so I'll give you one here. So what if I have, this is an example here. What if I have 2x squared minus 3x minus 9 over 4x squared minus 12x multiplied by x cubed minus 2x squared over 3x squared minus 6x. So this is a multiplication example. So with rational expressions, you can add them, you can subtract them, you can multiply them, and you can divide them. So what's the first thing we have to do if we can, and most likely we will be able to, is factor as much as possible. Factor as much as possible. So then the first thing is, hey, can I factor? What are the fraction the expressions here that I can factor quite easily? So the first one here, the first expression here is a trinomial. So we have to apply the AC method. So we can do that last. Can we factor this quickly? Can we factor these guys here a little bit faster? So how do we factor, for example, 4x squared minus 12x? What's the GCF? 4x. That's right. So 4x, and I'm left with x minus 3. Good. Next. X cubed minus 2x squared. What can I factor out of this one here? I can factor out a what can I factor out? An x squared. That's right. So I get x squared, x minus 2. Good. How about the denominator? I can factor out a 3x. So this becomes 3x. This is x minus 2. Okay, good. Good. So you start to see, hey, I have x minus 2 at the top and the bottom. And now we're left with 2x squared minus 3x minus 9. And how do I deal with the 2x squared minus 3x minus 9? How do we factor this? Remember the AC method? 2 and 9. Okay, so if I multiply 2 and I multiply by negative 9, I get negative 18. What two numbers multiply to negative 18 but give me negative 3 when you add them? 6 and 3, which one is negative? Negative 6 and 3. Good. So then I can rewrite this as 2x squared minus 6x plus 3x minus 9. And what can I factor out? A 2x, this becomes x minus 3. A 3, this becomes x minus 3. So I can factor out the x minus 3, and I'm left with 2x plus 3. So then I get x minus 3 times 2x plus 3. And now, once I factor everything, I cancel as much as I can. And what do I cancel? The things that are in the top and the bottom of this product. So the x minus 2s, I can cancel. The x minus 3s, I can cancel. I can also cancel out the x's here. I got one x here, and then I got another x here that that cancel out. So then what's the final answer? Final answer is 2x plus 3 is the only thing that appears on the top. And on the bottom, I got 4 times 3, which is 12. So that's it. I've I've canceled everything as much as I can. So I can leave it like this. And if I want to, if I can also separate the fractions. And I'm left with x over 6 plus 1/4. So either way is fine. I can leave it like this, or I can separate them if needed. Okay. Make sense? How would it be 12? Oh, how is it 12? Well, when you multiply fractions, when you multiply, so okay, when you multiply a fraction, you're multiplying. So actually, I should be more specific. When I do these cancellations, what's left is like 1. And when I multiply fractions, I multiply numerator by numerator, denominator by denominator. So I'm really multiplying all these things together. And the result of multiplying 1 times 2x plus 3 times 1 times 1 is just 2x plus 3. But when I multiply the denominator, everything here, that the only thing that survived the cancellation process is the 4 on this denominator and the 3 on this denominator, and I'm multiplying. So this is a key operation here. I'm multiplying. So if I'm multiplying two fractions together, then the 4 and the 3 are multiplying. That's why I get the 12. Do you see that? Yep, I know. All of this stuff is amazing, isn't it? So this is a multiplication. Shouldn't it be 2x? Wait, you say 2x squared? Should it be 2x squared? What should be 2x squared?
When you multiply 2x plus 3, and then there's one more x on the right.
Well, the thing is, we canceled out this x squared with these two x's that I have here.
But there's only one x, so you cancel x squared out with 2x on the 4x and 3x. Is that what you mean?
Yeah, so the 4x and the 3x, right? This x cancels out one of them, right?
Uh-huh.
But there's an x on the bottom here.
Oh, okay.
You can also cancel this way as well. You can also cancel. So you have two x's actually in the denominator that are being multiplied with one another. So in a way, you can also do this. 4x times 3x, that's 12x squared. So this x squared are gonna cancel out.
Oh, okay, I see.
Okay.
Thank you.
No problem. Okay, good. So I think we got that down. So what happens now? What happens if I get something like this? 2x plus 1 divided by 2x squared plus x minus 15 divided by 6x squared minus x minus 2 divided by x plus 3. So what happens when we divide fractions again? What's that step that we need to apply before we do anything? Flip, but we keep this, right? We keep, we change, and we flip. So we keep the first fraction alone. So we get 2x plus 1 over. And now let's just factor this if we can. Not actually, you know what? Let's leave it. So this is 2x squared plus x minus 15 multiplied by x plus 3 divided by 6x squared minus x minus 2. So I flipped the second fraction, which is what we had to do. Okay, so now this becomes exactly like the problem we just did. And again, this is division. This is when we divide rational expressions. Multiplying is probably the easiest of the operations. Division is the second easiest. And then when we add and subtract, they get actually harder. So it's interesting how adding and subtracting rational expressions is a bit more complicated than multiplying or adding them or dividing them. Okay, so I flipped it, and now what? I have to factor. Can I factor? What is 2x squared plus x minus 15? I have to multiply 2 and -5, 2 and -15, and I get -30. What adds to -30, multiplies -30, pardon me, that adds to +1? 6 and -5, good. So this becomes 2x squared plus 6x minus 5x minus 15. Factor by grouping, this becomes 2x, x plus 3, minus 5, this is x plus 3. So this becomes x plus 3 multiplied by 2x minus 5. So this becomes 2x plus 1 over x plus 3 and 2x minus 5. And then what does 6x squared minus x minus 2 become? You can factor these here. Somebody say this is 1 here. This is 2. So when we factor this is 6 times -2. This is -12. And then you can make this into what? 6x squared minus 4x plus 3x minus 2. You can factor out a 2x and I get x minus 2. Factor out a plus of just the 1. This is 3. Wait. Sorry, this is 3x minus 2. This is 3x minus 2. And this becomes 3x minus 2 multiplied by 2x plus 1. So this becomes x plus 3 over 3x minus 2 multiplied by 2x plus 1. And then what happens? The 2x plus 1's cancel, the x plus 3's cancel. And what's left is simply a 1 on the top because all these become 1s. And I get a 2x minus 5 multiplied by a 3x minus 2. And that is my final answer. And if you want, you can expand it on the bottom. You don't have to though. Okie dokie. So guys, this is just review, guys. Remember, just review. We haven't even started the actual pre-calculus curriculum, but this is much needed to get, your engines going and getting into the right skill set that you need for the remainder of the course. Okay, so I'll finish here. I'll stop the recording and you should be able to have this for future reference.